Okay, time to begin. We are all here, so I will jump right into it. We're going to talk today about some mechanisms of heat, try to get into a little heat engine stuff. Next class period we'll do more heat engine stuff, and I'll have Tyler help me out doing some demonstrations of like a Hero's engine and stuff like that. So, starting off, Joule's experiment. Now, Benjamin Thompson, also known as Count Rumsford, was drilling cannon barrels, and he noticed that the cannon barrels got hot when he drilled them. I think we've probably all experienced something to that effect. And that made him start to think, hey, maybe this isn't what we thought it was. Because when I'm drilling the barrels, I am doing work. Right? I'm applying force and moving material. And so he said, I think that there's, the heating might be caused by me doing work. Now, we've already talked about the fact that calories are an energy. So I'm going a little bit back in time here. It was James Prescott Joule who did the experiment to show the equivalence between heat and energy. And so his experiment is illustrated here. You have a mass that is, okay, I got to go to the pointer. A mass that hangs down here, goes around a pulley. What does the pulley do? Basically, it's just going to change the direction of the string. And remember, the string is going to apply a force equal magnitude to the tension that's going away from whatever it's touching. So the tension is pulling up on this mass and pulling to the right on the top of this little beater. So there's a wheel up here on the top that the string is wrapped around, and then it goes down. There's the beater and the water. And then he has an insulated container, and he measures the temperature of the water. Now, according to conventional theory, if you put heat in, the temperature goes up. And the relationship between that heat and the amount of temperature change has to do with the specific heat and the mass. So if you know how much water you have, and you know it's water, so it has a specific heat of 1 calorie per gram degree Celsius, then you can know how much heat went in by measuring how much the temperature changed. So then he lets go of this mass, and of course when he lets go of the mass, gravity takes over. And what does gravity do? Okay, so gravity pulls it down. So we have a force of gravity that goes like that, and we have a distance like this. And so work is equal to force, gravity times the distance, which is parallel. That's how much work was done. And so that work is going to have units of kilogram meters per second squared, or times meters, or Newton times a meter, or a joule. So he calculates how much work he did on the water by measuring that mass dropping. And then he measures the change in temperature and calculates how much heat was added to the water. And from that, he got the relationship that 1 calorie is equal to 4.186 joules. Now, something that's troubling to me is that depending on the textbook you look at, you'll see different numbers there. 4.186 is, 4.1859 or something like that, is the official value used by the NIST, National Institution of Standards and Technology. But you'll see different numbers. 4.184 is very common as well. I don't know why exactly. I should study that again. But that's just showing us the equivalence between a calorie and a joule. Now, we already talked about dietary calories. How does a dietary calorie relate to a joule? Or relate to this calorie? Yeah. 1 dietary calorie, which we write with a capital C, is equal to 1 kilocalorie, or 1,000 calories, and thus 4.186 joules. So there's a whole lot of energy when you eat a candy bar. It's a very enormous amount of energy, which is why you can fuel your body. If you eat 10 candy bars a day, that's all you need in terms of energy. That's more than you need in terms of energy. And trust me, I can eat 10 candy bars in a day. Now, just because we want to make sure we all know this, you need not just energy, you also need nutrients. You're not going to get the nutrients from those candy bars. So you can't go on a diet of candy bars. Look, I have 3 for breakfast, 5 for lunch, 2 for supper. I'm good to go. No, it's not going to keep you healthy. I just have to point that out in case somebody says, I really learned something in physics today. I learned about how I can be unhealthy. Okay. The experiments of Joule that showed that heat was just a form of energy led William Thomson, also known as Baron Kelvin. I wish I was titled so I could be, Richard Webb, Baron, something, but of course I'm not titled. I assume none of you are titled, but if you are, cool. And also highly unusual. So William Thomson used this to do some energy balance and come up with the first law of thermodynamics, which is extremely important in all of physics. The first law of thermodynamics says that energy cannot be created or destroyed. It can be shifted from one type of energy to another. You can have mechanical energy, which there were 2 types of mechanical energy we talked about. What were the 2 types of mechanical energy? Potential and kinetic. So you can have those 2 types of mechanical energy, or you can have energy in a bunch of material, what we call internal energy, or thermal energy, or you can have sound energy, or light energy, or chemical energy, but you can't create or destroy it. You can only move it from one type to another. There's another type of energy that seems really bizarre. This was something that Einstein came up with, and that's mass energy. Before 1905, people took as a completely separate fundamental rule that mass can't be created or destroyed. Much like the song goes, nothing comes from nothing. Well, that was taken to be, mass couldn't be created out of nothing. Well, Einstein actually said, no, mass is just a form of energy. So we can't actually make mass out of nothing, but we can have energy like light, and we can convert light into mass. How many people knew you could convert light into mass? Yeah, it's not very commonly known. Einstein was the one who came up with it. That's actually what the famous E equals mc squared equation is telling us. That famous E equals mc squared equation says that something that has mass has energy that's equal to its mass in kilograms multiplied by the speed of light squared. And that's the energy just because of the mass. Not motion, not anything else, not chemical energy, just because it has mass. So, the first law of thermodynamics, energy can't be created or destroyed. Now, to write this out as an equation, because we love to write equations in physics, you've learned that, right? We say, okay, let's talk about the internal energy of something. We'll call the symbol U the internal energy. So that internal energy is going to include the kinetic energy of molecules moving around, the energy of bonds holding molecules together, those kinds of things. All of that is included in the internal energy. And then if energy can't be created or destroyed, the internal energy can only change if you put energy in or take it out. And we have 2 mechanisms for transfer of energy. One of them was work. It's a transfer of energy due to what? Or involving. If I'm going to do work on this, if I hold it like this, I'm not doing any work. Why? Doesn't move. Work, you have to have motion. So work is a transfer of energy involving motion. And then the second transfer of energy is heat. which is a transfer of thermal energy, or as I simply say, it's a transfer of energy that doesn't have the motion in it. So when you have light shine on you and it warms you up, that's a heating process because there's no motion involved. And so that first law of thermodynamics, saying energy can't be created or destroyed, we say the change in internal energy, delta means the change in, has to be the sum of those two. Now, I did not put signs for a very specific reason. We have some sign conventions that can be confusing. We define heat as heat added. So Q is the heat added. Well, if I add heat, what happens to the internal energy? Is it going to go up or go down? If I add heat, the energy came in, so the internal energy goes which way? Let's talk about money in a bank account. If I put money into my bank account, what happens to the balance? Does it go up or down? Up. Right, so if heat is added, then the internal energy goes up. So there's a plus sign there. Whoops. A plus sign there for the heat added, because if you add heat, the internal energy goes up. For the work, we define the work as the work done by the system. So that is, the system did work on something. So if I come over and I push on Tyler's book, I did work on it. Did energy go into me when I did the work, or did energy go out? It went out. So going back to the bank account, if money goes out of your bank account, what happens to the balance? It decreases. So since we define work as the work done by the system, then it has a minus sign there. Some textbooks, instead of talking about the work done by the system, they talk about the work done on the system, and that changes the sign. So you have to be careful. If you look at other resources, you might see this with the signs changed because they used a different definition for what work they were putting in their equation. So the really key thing is energy isn't created or destroyed. And then we talk about the ways that energy can be transferred, and we get this equation. So that's our equation for the first law of thermodynamics. It's very important. The second law of thermodynamics, I'm just going to say it now so I don't forget to say it at some point. The second law of thermodynamics says one statement I've already made. There's like 5 common statements for the second law of thermodynamics. One statement is that heat always flows naturally from a hotter thing to a colder thing. We've talked about that. Does that make sense to you? How about a refrigerator? What happens in a refrigerator? It's the other way, right? A refrigerator, you're removing heat from the cold area inside the refrigerator and depositing heat in the hotter room. So a refrigerator is going backward from that. It's not a violation of the second law because that wasn't natural. You have to do things. You make what we call a heat pump to make the heat go the other direction. So that's one statement of the second law. Another statement of the second law is that things tend to go to the lowest potential energy state possible. Another statement of the second law is things tend to go to the highest entropy possible. You probably have heard that, right? Yes? No? No? Well, we'll talk about it a little bit later, not today. That entropy statement can be said another way, which makes a lot more sense than the simple mind, that natural processes tend to go to the most likely outcome. That makes a lot of sense. So the second law has a lot of statements. They're all tied in with the direction that a process is going to run. The second law is the only law in physics that specifies the direction something's going to run. Without the second law of thermodynamics, it would be perfectly acceptable for this thermos sitting on the table to suddenly cool the table and shoot up into the air. That would violate nothing in physics except the second law of thermodynamics, which basically says that's really unlikely to happen, because that would require heat to flow. Two things are same temperature, should be no heat flow. Flows from one making it colder into the other making it hotter, and then that energy is converted into kinetic energy. It's never going to happen, but it's theoretically possible. The second law is the one that says it's not going to happen. Yeah, here's where I just defined what internal energy was. It's the sum of the kinetic and potential energies of the atoms and molecules making up the system. Okay, moving on. First clicker question. A hot plate is used to transfer 400 calories of heat to a beaker containing ice and water. 400 joules of work is also done by stirring. Question is, what's the increase in internal energy in the ice-water mix? Since I actually have this doing percentages, having only 8 people answer will make my work easier. But not your grade. Okay, so what we had was 4, 2, 1, 1. The plurality here, 4, is correct. Let's go through how that's correct. So we have first law. Energy is not created or destroyed. We can say that not created or destroyed in one word. Conserved. Conserved means it's not created or destroyed. So energy is conserved. If we look at this, a hot plate is used to transfer 400 calories of heat to a beaker. So we have the heat added is equal to 400 calories. And then we have work done on the system is equal to 500 joules. Those are different units. So I can't just add 400 and 500 because they're different units. So I have to convert them. That's why I have 1 calorie is 4.186 joules. So I take this 400 calories and multiply it by 4.186 joules per calorie. And that's going to be 1680 joules, I believe. Now, notice I had heat added and work done on the system. If the work is done on the system, is that energy going in or going out? If it's done on the system, it's going in. If it's done by the system, it's going out. I don't mind that you're wrong, because it's getting these ideas in your head that's the important part. It's not being right the first time. So if the work is done on the system, it's added to the system. So I'm adding both of these. So the change in internal energy, it's Q added minus work done by, I got an extra loop on my work, which is the same as Q added plus work done on. So that's going to be 1680 joules plus 500 joules equals 2180 joules. So that's how we got that far. Now the next question, next one's a clicker question, is going to build from this. So we're going to start with the 2,180 joules and heat water. Melt ice. So melting ice, we have a relationship between the heat that we put into ice and how much it melts. So we're starting with ice at 0 degrees. We don't have to heat it up at all. We just have to melt it. How much ice can we melt with that amount of heat? Okay, we had 7. Now, the 7 are correct. Even though the 7 are correct, there could have been people who guessed at it, and there's one that didn't, so let's go through the process. We learned last class period on Monday that in order to change the temperature, Q was equal to MC delta T. But in order to change phase, Q is equal to ML. And if it's melting or freezing, it's latent heat of fusion. So in this problem, we have Q, we have L, so we just solve this for the mass that can be melted. And I'm trusting, I didn't do the math right now, I'm trusting my math from previously, that's 6.5 grams when I divide the two. So that's how we found how much ice could be melted from this heat added from the hot plate and from stirring. So yes, you can melt stuff by stirring. I argue with my wife, she just likes to leave the fan on all day long when it's hot. I say, but you're leaving that fan on. The fan is stirring the air. That's adding energy to the air, and you're very slowly heating the house up with the fan on. Now, when you're present, it's nice to have the fan on. It's nice to have the fan on because it blows air over your body and helps your body to have evaporative cooling more efficiently. That is, you have a little moisture on your skin. Only the hottest molecules can go from liquid into vapor, and the cooler ones then remain, and so you're cooler when you have evaporation occur on your skin. If you have wind blowing by, it takes that water away, so evaporation occurs more rapidly, and thus it makes you feel cooler having a fan on a hot day. But if the room's just closed up, that fan's just going to heat up the room. So when you're out of the room, it's best to have the fan off. But it's not going to be a huge temperature change, just something that causes friction in my life. Work. I'm working right now, right? I'm doing my job. I'm talking, hopefully passing on information in a way that will stick with you and you'll understand. In physics, we had work was a very specific meaning, one we've already talked about, force times the distance parallel. Now, if we talk about a gas, when we talk about the gas, instead of talking about things like force, we often talk about things like pressure. We introduced pressure before break. Pressure is the force per unit area. So in this picture up here, we have a gas container, and there's a certain pressure on the gas, and it's built to look like a piston. And so to hold the piston in place, you have to put a certain force on that piston. And you can calculate the force just like we did before break, that the force that you have to put on the piston to keep it from sliding is equal to the pressure in the gas multiplied by the area of the piston. Everybody remember that? Everybody remember the time before vacation? Trust me, it existed. Well, since we know the force that's necessary to hold it there, if we push the piston in, then we're going to have a force on the piston and a distance it moved parallel to that force. By definition, that means we do a work on it when we push the piston in. We do a work, our force times distance is positive, so we put energy into it. Well, first of all, if I push it in and I put energy into it, what's going to happen to the internal energy of that gas? If I compress it, what's going to happen? Okay, pressure does increase, but my question was about the internal energy. If I do work on it, what happens to internal energy? Or we talked about the bank account, it's going to go up. Well, if it's a gas, it's not going to be changing phase, so if it's not changing phase, I have Q equals mc delta T. If I put energy in, the energy is going to go into heating it, and the temperature is also going to go up. So when I compress that gas, the temperature is going to go up. And you probably have noticed that. How many people have pumped up a bicycle tire with a little hand pump? Okay, well, not everybody. Well, when you do that, what happens to the pump? It gets hot. And it gets hot because you're repeatedly doing this. You're repeatedly compressing that air. And when you compress, you're doing work on it, the temperature goes up because that work is being put into raising temperature and raising the pressure, as Tyler said. When you're pumping up the tire, it's the pressure you're more concerned about, right? But it gets hot because of that work done. So how much is the work? Well, we've learned, work is equal to force parallel to the distance. Well, if I push this in some distance d, they're parallel, and so that would be my force, pressure times area, times the distance d. But I have a change in volume for my gas. And the change in volume is equal to the area multiplied by the distance I moved it. And so this area multiplied by d is change in volume. So the work is equal to pressure times the change in volume. Now there is, once again, some sign conventions you have to pay attention to. If the change in volume is, well, in this case here, if I compress it, was that a positive change in volume or a negative change in volume? If the piston is compressed to make it so it's smaller. It's a negative change in volume. And so if I have a negative change in volume, then energy was going in, right? So that means that for a negative change in volume, the work done on the system is positive, the work done by the system is negative. So we usually define this as the work done by the system, and then we leave with all positive signs. So if it expands, the work done by the system is positive. If it contracts, the work done by the system is negative. And that's why the traditional signs for delta U is equal to the heat added minus the work done by. We put the minus sign here So we can put that in with positive signs. So what's the importance of this? We can now calculate the work done on a system by looking at the pressure and the change in volume. Notice it's pressure times change in volume. Not the change in pressure times volume, not the volume times the change in pressure. You have to have a change in volume to have work done. So, here's my slide that does what I just did. The work done by the system is equal to pressure times change in volume. Okay, so I already did that. Clicker question number 3. This, of course, is going to have to do with work done on the system. You have to pay attention to that direction. So which statement is true about the work done on the system? The system is the gas. When you push the plunger down on a bicycle pump. Okay. And you can see why I've talked so much about this. Even with all I've talked about it, it's still not perfectly clear. The 6 are correct. When you move the plunger down, delta V is negative. You've decreased the volume. And so the work done by the system is P delta V, and therefore negative. The work done on the system is minus the work done by, and therefore positive. Paying attention to those signs, well, obviously it's going to be the difference between right and wrong. So it's kind of important. If you have questions about those signs, do ask. Okay, ideal gases. What's ideal about an ideal gas? An ideal gas behaves in some fashion that makes it really easy for us to work with. What things make it easier for us to work with? If the gas molecules have perfectly elastic collisions. So an ideal gas, you have molecules with perfectly elastic collisions. Perfectly elastic means that you have no loss of kinetic energy when you have a collision. So in practice, that means that they don't stick. If I have two things hit each other, they just bounce off with no stickiness whatsoever. So that's one thing that's ideal. Another one that's ideal is if the molecules actually are so small that they don't interact with each other at all. So if I have two molecules that come by, they're small, no forces between them, like no, at this point we've learned about gravitational force, force of distance. Masses would have to be small. If they just go by, they don't even interact. Those are the two things that we want for something to be ideal. Now they're not real because molecules are always going to have some kind of interaction if they get too close. But if they're going fast, that interaction is going to be pretty small. And if they're going fast, that means they have a high temperature. So gases are more ideal when they're at higher temperature. Another thing about them not colliding or not interacting, if you only had one molecule, it would never interact with another molecule, right? And so the lower number of molecules, or we usually talk about the lower number of molecules per unit volume, the more ideal it behaves. So basically, for something to behave ideally, we say high temperature and low pressure. High temperature is a relative term. How do I define high temperature? If it's well above the boiling temperature, that's high temperature. So if I have water has a boiling temperature of 100 degrees Celsius. So steam, water vapor, at 105 degrees Celsius, not close to ideal because it's pretty close to the boiling temperature. Steam at 500 degrees Celsius, very close to ideal because it's well above the boiling temperature. Now, for air, what's the primary component in air? Nitrogen, 79% nitrogen. The boiling temperature for nitrogen is 77 kelvins. Room temperature is way above the boiling temperature for nitrogen. Hence, room temperature is hot, high temperature compared to the boiling temperature of nitrogen. So air behaves as an ideal gas at room temperature, provided you have a reasonably low pressure. If the pressure gets too high, if you have room temperature, but 100 atmospheres of pressure, that's 100 times the atmospheric pressure that we normally have, yeah, that's not going to be ideal. So you have those two things about what makes a gas ideal. If you have an ideal gas, then the internal energy is absolutely proportional to the temperature. Remember I said kinetic energy is a measurement proportional to the average kinetic energy. If you have an ideal gas, if it's a monatomic ideal gas to be exact, then you have the internal energy is equal to the number of molecules N times the average kinetic energy of the molecules. And for an ideal gas, the average kinetic energy is equal to 3/2 some constant multiplied by the temperature. By the temperature. What units do you suppose you should use for temperature? It actually has to be an absolute temperature. So the average kinetic energy is 0 at absolute 0. So it needs to be kelvins. You could also say Rankine, but nobody uses Rankine ever. So kelvins. So that means our internal energy for the ideal gas is 3/2 times the number of molecules times this constant K multiplied by the temperature. That constant K is just the Boltzmann constant. I believe there's 2 N's in his name. And I'm not even going to worry about writing down the number right here. So for an ideal gas, what I've been saying about temperature is absolutely true. It's a number proportional to the average kinetic energy of the gases. For something that's not an ideal gas, there's still a proportionality. It's just the proportionality is not a simple proportionality like this. You have like an offset, right? You go into the solid, you have some energy associated with the bonds between molecules, and so it changes and becomes different. But it's still, if you increase the temperature, you're increasing the average kinetic energy. I feel like I'm going through a lot of different topics here that aren't super well connected. Here I have this word adiabatic. An adiabatic process, adiabatic comes from the Greek word, it means basically no flow. An adiabatic process is a process where heat does not flow. So is it possible to have an adiabatic process, a process where heat does not flow? The simple answer is yes. It takes time for heat to flow. I'm going to end my lecture talking about how heat can flow. And there are 3 mechanisms for heat to flow, but all of them take time. And so if I have a process that occurs really quickly, there's not enough time for heat to flow. And so a quick process can be adiabatic. Or if I have a really well insulated system, insulated so heat cannot flow, I can also make an adiabatic process. Adiabatic is not the same as constant temperature. Because imagine I have a gas, and I compress the gas really quickly. If I do it really quickly so no heat can flow. But if no heat flows and I compress it really quickly, we said that the temperature has to go up. The temperature went up because the energy that I put into it went into making the molecules move faster. But I didn't have any heat flow out. I didn't have any energy lost from heat flowing out. well, there are a lot of simple phenomena you see with these kinds of adiabatic things. If you take a soda bottle and you open it, the gas in there will expand rapidly. And when it expands rapidly, if it's a nice cold soda, when it does the rapid expansion, it's just the opposite of when I compress gas. What happens to the temperature when I compress gas quickly? It goes up. So if I let it expand quickly, work goes out, the temperature is going to drop. Well, when the temperature drops, the amount of moisture that the air can hold drops. The amount of moisture the air can hold actually changes very dramatically with temperature. So when it's cold, the air just can't hold much moisture at all. When it's hot, it can hold huge amounts of moisture. So you have this cold soda, it's what we call saturated inside there because you just have the liquid and the gas, and you have an equilibrium that's been set up between the gas and the liquid. So you have as much liquid in the gas as it can hold. You open it up, it expands and cools, so now it can't hold as much liquid. But it didn't just lose the liquid, and so that liquid quickly condenses to form water droplets. And when it condenses to form water droplets, what do you see? No? It looks like a cloud, because that's what clouds are. Clouds are droplets of water in the air. And so if you have a nice cold soda, and you take that cap off, oftentimes you'll see it looks like, well, we say steam. It's a little cloud coming out. Because you had the water that was in the vapor inside the bottle, it suddenly cooled and couldn't hold that much water, so it formed droplets. The water in the air is not in droplets, it's just molecules of H2O mixed with primarily nitrogen. Secondary feature, of course, is oxygen in the air. And by the way, since I said 79% nitrogen, roughly 20% oxygen, which has an even colder boiling temperature than nitrogen. Okay, I spent a lot of time on that. Talk about two more processes, isothermal and isobaric. Isothermal means constant temperature. So we have processes that we do in thermodynamics with constant temperature, things where we have water. We have this water at 60 degrees Celsius. And we maintain the water at 60 degrees Celsius and we put a vessel inside and do stuff in that vessel. Because the water is going to keep the same temperature, I have an isothermal system, as long as I go slowly. If I go quickly, well, I can break it. Isobaric is constant pressure. If you take chemistry class, pretty much everything you do in chemistry class is going to be isobaric because you do them out in the open. So you have atmospheric pressure all the time with your chemical reactions. So that's an isobaric process if you have constant pressure. Now I do want to get to the, for an ideal gas, we define the equation of state that relates what we call the state variables. Now, when I talk about a ball, I have a ball, and I throw this ball. The variables that I would use to talk about this ball would be things like its mass and its velocity, right? If I know its velocity in the three directions and its mass, I know its kinetic energy, its momenta, everything. So those would be the equations of state if I had just a ball. If I had three balls, I would have to have those variables for all three of the balls to know everything that's going on in my system. But if I know all those things, I can know, oh, they're going to come, they're going to hit, this is going to happen. I can calculate everything. We call this deterministic, if I can calculate everything that's going to happen. Well, what if instead of three balls, I have three googles of balls? And a google is 10 raised to the 100th power. That's a whole lot of balls. There's no way I can do the calculations on what's going to happen with those balls, right? Now, in this room, we have somewhere in the ballpark of 10 to the 25th molecules. It's not a google of molecules, but it's a big number of molecules. There's no way I can calculate what's going to happen with each one of those molecules. That's why we do thermodynamics. Thermodynamics is applying statistics to all of those molecules. So thermodynamics is also called statistical physics because you're using statistics. And with those statistics, instead of talking about the mass, velocity, etc. for each ball, we talk about these variables of state, the pressure of the system. So that's variable number 1, pressure. The volume of the system. The number of molecules in the system. And of course, the temperature of the system. So those 4 variables we call the variables of state. I can talk about my system just knowing those 4 variables instead of knowing billions upon billions upon billions of variables. And then we use statistical calculations to determine what's going to happen. And an equation of state is an equation that relates those variables of state into one equation. So the ideal gas law shown there, PV equals NKT, is the equation of state for an ideal gas. That tells us how these state variables will relate to each other. This comes from looking at things like Boyle's law. We already looked at Boyle's law, at Gay-Lussac's law, at Charles' law, and combining them. K is just a constant. Now, some of you may have seen a similar law that was called the ideal gas law. How many people know the ideal gas law with a slight variation? Was that? It's like we're in an auction. Denver tips his hat. Means he just bid, right? No? Well, a lot of people know the equation PV equals nRT. It's only different in 2 things. We have a lowercase n, and that's the number of moles. What is a mole? 1 mole is equal to 6.022 times 10 to the 23rd molecules. So that's just a different unit to tell us how many molecules are present. This number 6.022 times 10 to the 23rd molecules, that number has a name. It's Avogadro's number. I think it's AVO. Or a symbol N sub A for Avogadro. So we've changed from talking about the number of molecules to the number of moles, which is just a different unit for number of molecules. So what is R? R is the ideal gas constant defined as R is equal to K multiplied by Avogadro's number. So N is the number of molecules divided by Avogadro's number. R is K times Avogadro's number. Thus, NR is equal to and you see canceling out. Lowercase n times R is equal to uppercase N times K. So that's the ideal gas law. It helps us to, or allows us to, at any time, if we know the pressure, volume, and number of molecules, we know the temperature as well. That's the beauty of that equation. That's its usefulness. Okay, now we're going to talk about heat in our WOW. Maybe we won't talk about heat in our last minute. I guess we'll talk about heat next class period. We'll have Tyler talk about everything. But I want to end with this question. Why are houses insulated with spun fiberglass rather than just empty space? And obviously I don't expect that you necessarily know the answer. This is to see what you think. So we had 6 people said to reduce conduction, 2 said to reduce convection, and none said to reduce radiation. Next class period on Friday, we will carefully look at what conduction, convection, and radiation are, and then we'll be able to come back to this and discuss what the correct answer was.